Hello everyone. In lecture 61 of Principal Electric Circuit, we will introduce a new concept, phasor. Phasor means the vector with the information of phase. How's it born? We'd like to show you the example to help understanding. In the first order RL circuit with a sine excitation, we want to find the steady-state solution of IT, ULT, and URT. For the dynamic circuit, we can easily list its equation. That is, L time di over dt plus R time I equals Us equals Um times sine omega t plus psi u. It's the same as the time domain analysis of dynamic circuit discussed in the previous 3 weeks. As we know, the time domain expression of the current equals a steady-state solution of the current plus A times e to the power of minus t over tau. A times e to the power of t over tau is the general solution of the homogeneous ODE, where A is the underdetermined coefficient and tau means L over R for RL circuits. What interests us now is its steady-state solution. We made discussion on conditions that the excitation is a polynomial function of t or a constant. On the sine excitation condition, the steady-state solution of the current can be written as A times sine omega t plus B. To solve A and B, we need to substitute them into the equation and compare the corresponding coefficients. Before the substitution, we need to make a differential first, and it equals A omega times cosine omega t plus B. Substituting these two expressions into the equation, we get that LA omega times cosine omega t plus B plus RA times sine omega t plus B equals sine omega t plus psi u. The left expression can be simplified. First, we take A out and times and divides the square root of R squared plus omega L squared simultaneously. Then we need to simplify the expression to sine omega t plus some angle. Obviously, we need to simplify the left one to a cosine and the right one to a sine. The angle in the sine and cosine are arctangent omega L over R. Then we can get that A times the square root of R squared plus omega L squared times sine omega t plus B plus arctangent omega L over R equals times sine omega t plus psi u. We compare the corresponding coefficients such as the amplitude, the angular frequency, and the initial phase angle respectively. Then we can find out that A equals a square root of R squared plus omega L squared, and that B equals psi u minus arctangent omega L over R. Then we get a steady-state solution of the current. It can be expressed like this. After that, we can get the steady state of solution of UL. For UL equals L times di over dt, we can substitute the expression of the current into it and get that L omega times UM over the square root of R squared plus omega L squared times sine omega t plus psi u minus arctangent omega L over R plus 90 degrees. It should be a cosine here after the differential, and we express it as a sine for the uniform by any 90 degrees. Next, we need to find the steady state of UR. As we've obtained the steady state solution of the current, UR can be expressed as R times I, or solving it by KVL. That is, UR equals US minus UL. By KVL and trigonometric transform, UR can be expressed like this. Then we finish the whole solution. Got a picture? It seems like we make it, but it's a hard way to make it through. After all, there are three difficulties when solving it. The first is it's complicated to find coefficients for the special solutions of the current differential equation. The second is not easy way to get the voltage of the resistance, for we need to make calculations among sinusoids by trigonometric transform. Finally, we need to make complex differential of sinusoids when finding the voltage of the inductance. In other words, we need to make complex integral of the sinusoids on some conditions. Maybe this is not a problem for you, but how about this one? We've introduced the power system in lecture 60. It's a connection diagram of basic power substation in China. Every red line represents a source. You can regard it as a sine voltage source. This is another sine voltage source. Every blue line represents a load. The load can be replaced by a RL circuit on usual. Here are 10 outputs, which means we can have 10 RL loads. Every yellow line also represents a load. It's a RL load 2. Namely, in such a basic power substation, there are two sources supplying power to 13 loads. Every load can be modeled into a series of 1R and 1L. That means we need to list and solve a 13-order differential equation to get the distribution of power of voltage and current in the basic power substation. There's no easy way to find coefficients for special solution of these differential equations. To plus or minus between the sinusoids, to make differential integral of the sinusoids, and to get all the voltage and currents in this circuit, isn't there? Moreover, it's one of the simplest power substations. It's incredible to analyze the operation condition of the voltages and the currents in power system in China, even in the world. By the way, mentioned right now. So what can we do? We mentioned engineer Steinmetz in lecture 60, whose most important contribution is the phasor method of the steady-state analysis in dynamic circuits with a sine excitation. Let's analyze the simple circuit again by the way of Steinmetz given. We can find three branch variables, that is the current, the voltage of the inductor, and the voltage of the resistor. They have different amplitudes and initial phase angles, but they have the same angular frequency. It seems like a common sense. For a linear circuit, if the excitation has one frequency, then all responses in the circuit have the same frequency. But take thought deeply. What's the difference between the steady-state analysis in dynamic circuits with sine excitation and the analysis in pure resistive circuits? For a sinusoid, it's necessary to find three elements. That is the effective value, the angle, frequency, and the initial phase angle. But for resistive, for any branch variable, we only need the magnitude. With excitation, if a steady-state value in dynamic changes in same frequency, it's not necessary to find the angular frequency. Thus, Steinmetz created an amazing little thing to represent the effective value and the initial phase angle of a sinusoid. Do you think what is it?